I like sticking to this equilibrium because it's really important. We use it every day. So we were talking about making perfume. That was kind of a nice application that tied in with our organic. Here is another application. They take nitrogen from the air. They take hydrogen that they've extracted from methane, and they make ammonia. Now, ammonia is used to make ammonium hydroxide, which is then used to make fertilizers. Think about how many fertilizers we use in the world, in Alberta. So this is a huge industry. They also make soaps and bleaches and et cetera out of this as well, another huge industry. Okay, so this is really important to our economy. And not just our economy, many economies. And it's called the Haber process, is what this reaction is called. Now, people that are chemical engineers that are managing the Haber process factory had to figure out ways in which to shift the equilibrium so that they could make as much ammonia as they could. Because that's ideal. Ideally, you put in your nitrogen, you put in your hydrogen, all of it's used up and makes the ammonia. But because it's at equilibrium, no. Because as soon as you've made the ammonia, some of it decomposes into those two things again. So they had to use LeChatelier's principle to figure out how to make ammonia, as much ammonia as possible. So the first thing they can do is they can change concentration. Or one of the things, not necessarily the first, but one of the things. If you're changing the concentration, it's kind of a simple concept. If I add more nitrogen, or increase the concentration of nitrogen, if I add more nitrogen, I can make more ammonia. Everybody get that? Simple, right? You add more nitrogen, you get more ammonia. That's not really rocket science. And so the new kind of word we use is we must have shifted the equilibrium to the right because I made more ammonia. Or sometimes they ask you, you make more products this way, like they use products instead of ammonia. Or okay, so there's a variety of ways of saying this. And likewise, if I increase the, hydrogen, I would get more ammonia. Okay, again, not rocket science. Here, though, is where you kind of trick the system. If I decrease the concentration of NH3, which means that as soon as I put the things together, I make some ammonia. If I take it out of the system before it has a chance to decompose, I kind of trick the system. The system goes, whoa, where'd that ammonia go that I made? Oh, I'll make another one. Okay, so imagine you've got a bunch of Lego blocks and you're trying to put them together to make an airplane. And as soon as you've made your airplane, your big brother or sister takes it away. And you're not so clever because you're just a couple molecules. And you go, where did that airplane go? Oh, well, I'll make another one. And you put more bits together to make another airplane. And guess what? Your big sibling takes that one away. Oh, I guess I'll make another one. And meanwhile, they're selling these airplanes and making lots of money. Okay, this is what's happening. So if you decrease the ammonia, i.e. remove it as soon as you've made it, you will make more ammonia. So you are still shifting the equilibrium to the right. Okay? So taking away ammonia gives you more ammonia. Hands up if you're good with concentration. Good. What would happen if I decreased the hydrogen concentration then? What would happen to my NH3? I would get less. Which way is the equilibrium shifted? Shift to the left. So each time the equilibrium thinks, I need to restore balance again. Okay, I need to maintain that K value. If you've taken away your, you've taken away your H plus, it's going to want to replenish it. How can it fill it again? If I've taken this away, it wants to replenish it. So I'm going to shift it this way to fill it up again. Okay, Evan.
The chart system. Oh no, I read it wrong. Okay, never mind. I thought the chart said that it had no effect, but I read it wrong.
What does it have no effect on?
KC.
The K value. Why? Because it's trying to get back to the same K value. What's the only thing that can affect that K value from the ice tables that we've been talking about? The temperature. Right? And I was explaining this to Lindsay and Jillian. They said, well, is it just extra information? Like, no. How tall are you? I mean, to judge if your height is normal. How tall are you? 3 feet. Wow, you're short. Right? No, I'm not 18. I'm 6. Oh, age matters when you're talking about height. Okay, so I'm 3 feet and 6 years old. Now you can judge whether that's normal or not. I don't even know, I'd have to look it up, but okay? And it's the same with K value. This is the K value at the temperature. Why do they even give you temperature? Because it matters to people that know things about K values. It matters. Okay? All right. So the second thing I'll talk about is pressure. Oops. N2 and H2 and H3, 2 and 3. The increasing or decreasing the pressure is only affected if you change the size of the vessel or flask or whatever. Vessel's not spelled that way. How do you spell vessel?
E-L.
E-L, not L-E?
Yeah.
Okay. There is no change in equilibrium if I increase the pressure by adding more inert or unreactive reactive gas.
So the only way to change the pressure is to change the size of the vessel.
Right. So there's 2 ways to change the pressure in a balloon. One, I could squish it. That would change the pressure of the balloon. The other way is I could blow more air into it. That would also change the pressure. But like keep the volume the same. Right? Keep the volume the same, force the balloon. It's already blown up as high as it can. Now you try to blow more air into it. That'll increase the pressure. Okay? They both increase the pressure. But equilibrium is only affected if I am changing the size, if I'm squishing the balloon. Not about blowing more air in. Okay? Everybody okay with that? By inert gas, well, that's like nitrogen, helium, neon. Okay? In this case, though, for this reaction, it couldn't be nitrogen. As soon as I add nitrogen to the system, I'm back to the concentration discussion. So for this question, what would happen if you added some neon gas to the system? Nothing. Okay? What would happen if you had nitrogen? Now you're talking about the concentration. But let's go with size of pressure. Okay? So, this, I like to think of it as building blocks. This is the analogy I give. First of all, it only affects gases, which in this case, they're all gases. Gas, gas, gas. If I have 4 moles of gas on this side, everybody okay with that? 1, 2, 3, 4 moles of gas on that side, equilibrium arrows, and 2 moles of gas on that side. Okay? If I take if this is my balloon, okay, and I'm going to increase the pressure by decreasing the volume. So I'm taking this bar and I'm pushing it down. These building blocks are going to be affected the greatest. And so they will topple over and spill over onto this side. Okay, so what happens is you increase the pressure in the system, and it's the nitrogen and the hydrogen that feel that pressure the most. And you're increasing the pressure, and the equilibrium goes, whoa, whoa, let's decrease the pressure. They're like teenagers, right? Every time your mother nags, what do? You lay further back, right? I told you to clean your bedroom. It takes you even longer to clean the bedroom. Right? If you get the pressure increased, you tend to decrease the pressure. That's what equilibrium systems do. So you're increasing the pressure. These guys feel it the most. Why? Because there's more moles of gas on that side. And so it goes, whoa, whoa, I need to decrease the pressure. How does it do that? Well, you know what? If I react some of this up and I make more of this stuff, this side has less pressure. So overall, I'm balancing the system out again. That's what the equilibrium thinks. Okay? So an increase in pressure for this reaction, an increase in pressure would equal a shift right, which would equal an increase in the ammonia, ammonia concentration, and a decrease in the nitrogen and hydrogen concentrations. I hate this board. Everybody okay with pressure? All right. The third and final is temperature. When you're deciding the temperature, you have to know if it's exothermic or endothermic. Okay? There are two ways for me to teach you this. One is the proper way, where I explain it and you understand it, and the other is the cheat way. Right? I'll show you both, because some of us are going off to university, and some of us just need to pass. Okay? So here is the full way. N2 and H2 equilibrium, NH3 balancing it like that. This is an exothermic reaction. This way, reading it. The nitrogen and hydrogen coming together release energy. Okay? So, if I increase the pressure, increase the temperature for this reaction, it's going to go, whoa, whoa, whoa. It's hot in here. This way is making it hot, right? Going this way makes it hot. And you've just made it hotter. It wants to restore equilibrium. So what does it do? Goes the endothermic way. So this way must be endothermic. So if you increase the temperature, it will undergo the endothermic direction to decrease the temperature and restore balance again. And so for this reaction, that means I will make more N2 and I will make more H2. And I will make less, or I will be using up the ammonia. Does that make sense? And if I were to decrease the temperature, it's like, oh, it's cold. I want to make it hotter. So it does the exothermic reaction and shifts it that way.
So would it be like endothermic that way, exothermic that way then?
For this reaction, it's exothermic this way. If they tell you it's an exothermic reaction, it's how you're reading it, left to right.
So for what you're saying there, if it's too cold, then it would just be the opposite.
Right, so if I'm decreasing the temperature, is that what you're saying?
Yeah.
Then it'd want to shift it in this reaction. It'd want to shift it to the exothermic side, so right. Whereas this was a shift left. Yes, Rachel.
Okay, how come in the textbook then it says that like for the direction of the change it still uses products and reactants? Like how are you supposed to know? Wouldn't it vary?
Because in that table it says whether it's an exothermic reaction you're looking at or an endothermic reaction.
Oh, I see. Oh, okay.
So it's got two.
Yeah.
Okay. Everybody okay with that explanation? It's really handy because you understand why it does it and then you can apply it to more situations. But here's the cheat way. The cheat way is saying this. Okay, Raj, paying attention?
Yeah.
All right, so going back to unit 1, if it tells you it's an exothermic reaction, that means heat is produced or used up. So therefore it's a product, right? And if we had a number, like delta H equals negative 500, we put that 500 there. So now I'm going to put it as a plus E. Okay, so I'm just going to rewrite this. The N2 plus H2 equilibrium arrows NH3 plus E. And now I use the exact same knowledge, so that's knowledge based on unit 1. And now I'm back to my knowledge about concentration. Okay, so if I increase E, it's going to try to use it up. So it's going to shift in the left direction and produce more of these things. If I decrease the temperature, or E, it's going to try to replace it, therefore making more of this stuff. Do you get that? So you can, did you get the first way?
Kinda, yeah.
Okay.
So understand like what is it shifting? Like what's this shift?
The direction, the speed of how much is, in this case, if I'm shifting it, if we go back to the green, if I'm shifting the arrow to the right, I am creating more ammonia and decomposing less.
Okay.
In order
The
to
temperature is lower.
Because, yes, because I've decreased the temperature. Okay?
If you like decrease the temperature, though, wouldn't that like react less and there be less ammonia?
If I'm decreasing the temperature,
Yeah.
I'm using up E if I'm decreasing the temperature. So the system reacts
okay,
to
that
replenish it,
makes sense.
do more exothermic reaction to make more of that.
So that's the cheat. You're either using up, if the temperature's going down, you're using up E, if it's going up.
They're both the same thing. The cheat is writing the E as a product or reactant and then thinking of it like a concentration. They're both correct. It's just that this is sort of a bit more mathematical looking at it or something, and the other one's a bit more wordy. Okay? It takes practice. It takes practice to do these. So that's all we're doing the rest of the class today is practicing.